Yeah, let me start by thanking the organizers for the invitation to speak at this meeting, so this is an experimental talk. And as you will see, not all of our experimental goals are maybe perfectly well aligned with the main theme of the conference, but I hope that it will still be of interest to you. So, I will present experiments with iron crystals that are laser manipulated, and where one aspect is that we do some kind of variational optimization. And this is the work of two experimental teams at the University of Innsbruck and at the Institute of Quantum Optics and Quantum Information. And we have had also close collaboration both with local and international theorists with whom we have worked on these experiments. So what I want to do in my talk is to start out by giving you an introduction about ions as an interacting many-body system with single particle control. And then I will present you three recent experiments. The first one is about using a trapped ion quantum simulator for exploring large-scale entanglement of states that are variationally prepared. Then I will briefly talk about the possibility of doing spin squeezing experiments with spin lattice Hamiltonians that have finite range interactions. And finally, I will want to present you a new setup that we have been developing, where we go away from the long ion strings that we have been working with for about 20 years to two-dimensional ion crystals with more ions. But let's say we start with the introduction to our experimental setup. So we work with calcium ions, which have a radio frequency ion trap, and each of these ions encodes a quantum bit. And such a quantum bit can be encoded in a combination of the ground state with 1/2 level of calcium ion and the metastable state, which has a lifetime that is long compared to the duration of the experiment. And in this case, we have our qubit pseudo-spin system that we can manipulate with a very frequency stable laser that couples these two levels on a level-forbidden transition. And in order to read out then the result of this manipulation, we can carry out measurements by coupling one of these levels to a short-lived level, which decays rapidly back to the ground state and emits photons, and in this way, by observing the presence or absence of photon scattering, we can carry out a quantum measurement that projects our qubit with this energy Ising basis, which means that if we associate the bright state with the spin down state, the dark state with the spin up state, this would be the spin projection from the Z direction. Now, this fluorescence measurement can be done in a spatially dissolved manner, and if we have not single ion, many ions in a trap, then these ions, they will arrange themselves in ion crystals, for example, the linear string, as you can see here, and this opens up the possibility to manipulate these ions locally with a strongly focused laser beam that we can steer by moving it across the entire ion chain. And this single-qubit control can now be used, for example, to prepare states where we flip individual qubits into this non-person state for individual qubits, as you can see here. And I also showed you another example to show you that this is not just a random, it's not something which is random, but here we have a state which is, let's say, conjugate to the other state, where all the bright ions are in the dark state, as compared to the first state, except for the ground. Now, so we can use this for spin preparation, but we can also use it for measurements, in the sense that if we want to measure spin correlations or spin projections, other directions which are different from our measurement basis, we can carry out a single qubit rotation of any ion and measure any spin correlations in this way, which provides a powerful measurement tool. Now, so far this is a collection of qubits that are stored in an ion string, and now the question is how can we turn the system into an interacting quantum many-body system, which is the goal of our experiment. And in the absence of laser light, the only interaction that we have at our disposition is the Coulomb interaction between the particles, which is not state dependent on the internal state of the particles. But it's a long-range interaction which sets the equilibrium positions of the ions. So the ions at the locations where the neutral Coulomb repulsions balances the confining forces of the trapping potential, and also the Coulomb interaction gives rise to collective modes of motion of this ion crystal, similar to what you have when you have phonons in the crystal lattice. And so we have long-range collective modes of motion of this ion crystals, and in combination with laser pulses is a key for realizing then the interactions between the particles which depend on the internal state of the particles. The idea is that if you have an atom that absorbs a photon or that undergoes a stimulated emission process, then in this process there is a momentum transfer from the light field to the particle. So either a photon gets absorbed and then the momentum HRK of the photon gets transferred to the ion crystal, the ion gets hit, or if the ion is in the upper state, it has a stimulated emission process. Now there are two photons with momentum of 2 HRK, and then the ion gets taken in the opposite direction. So we have a state-dependent force when we work with lasers that couple them this way to the ion motion. Now, as I told you, this ion motion is a collective property of the ion crystal. And so, if we do it in the right way, then we can use laser light in combination with this long-range Coulomb interaction, to engineer interaction, which looks like an effective spin-split interaction. And this opens up the possibility to simulate lattice spin models with such a system of trapped ions. Now, for this, I briefly want to discuss the crystal geometry of these collective modes of motion. So if we have a long string of ions, then this string is produced by putting the ions into a harmonic potential which is very anisotropic. So we have then two directions in which the confinement is strong, and one direction in which the confinement is weak. And for this reason, the equilibrium positions of the ions are along the direction of the weak confinement. And in this case, you get collective modes of motion. You have n ions in the string, you have a set of n motional modes of motion where the ions move along the direction of the string. And then you have another two sets of n motional modes where the ions move in the transverse direction. And the transverse motional modes, they tend to cluster the frequency space of the higher frequency modes and the center of mass mode of motion where the entire ion string moves up and down, and then you have some bending, some tilt modes and bending modes and slightly lower. There's a similar picture if you look at two-dimensional ion crystals. In this case, you get 2 times n in-plane modes of motion, and there's one in the n out-of-plane motional modes that describe the ion motion perpendicular to the plane direction. Now, how can we use these motional modes in order to produce entangling interactions between the particles? And in its basic form, this is what you have in the proposal which was made more than 20 years ago by Anders Johnson and Klaus Möllmann, which imagined that you have 2 qubits that you couple, each of which you couple to a harmonic oscillator, quantum harmonic oscillator that describes the ion motion. And it's done in this way. So if we have just 2 qubits, we have 4 states that we need to consider. Both qubits spin down, both up, or one down. And on top of that, we have now the motional states of this quantum harmonic oscillator, 0, 1, and so on. We assume that we pull this motional mode to the ground state, and initially the ions are the down state. Then we can use now 2 laser fields, which have frequencies such that they couple close to these what is called vibrational side bands. So if you have a transition where you flip the state of 1 qubit, at the same time you increase the motional quantum number by 1 unit, and you couple the qubit to the motion. And this can be done by a laser which has a frequency which is tuned close to this transition. So we want to have some off-resonant process. It's a bit of a kind of 2-photon, 2-ion transition, where we have lasers with 2 frequencies, such that the sum of the 2 frequencies just matches twice the qubit transition frequency. And this way you see that we have a coupling between the spin down, and the spin up, which is mediated by these states in between that are only virtually populated. In this way, you get a coupling between spin down, spin up, spin up, spin up. There's a similar process that couples spin up, spin down, spin up, with the same coupling strings. And you see that in this way, you have here an interaction that, which first of all, if you have just a 2-level system here, can be used to create entanglement. If you have a coherent excitation, that you stop the transfer process halfway. And the Hamiltonian behind this looks like an Ising model where you couple the 2 strings with each other. Now, this works for 2 qubits, and it also works if you have a laser that illuminates an entire collection of ions, then you get also these pairwise couplings. In this case, the coupling is needed not only by a single quantum harmonic oscillator, but by all these transverse modes of motion of an ion stream. It means that this is an example of an 18 ion spectrum. We have here these take the spectrum, you see that you can inside here on the qubit transition, but you also see excitations if you tune the laser close to this variational side length, which here to the right in the transition. And if you have now this ultimate light field, which is slightly off present in all of these transitions here, you get exactly these processes where you start out with a pair of ions in the ground state, for example, the motion, one of the oscillators in the ground state. You transiently couple it to a state where the oscillator is excited, and then in the second step, excitation returns to the original state, and you flip them this field, this qubit. And doing this now results in a Hamiltonian, which looks like an Ising Hamiltonian with a spin-spin coupling matrix, which depends on which pair of ions you will. And in order to give you some more insight into how this spin-spin coupling matrix looks like, I want to show you a little example of how this coupling matrix arises. So I told you can easily calculate these couplings here in second-order derivation theory. So you have the product of the coupling strength from the first transition multiplied with the second transition divided by the tuning from the intermediate state. And you have to sum then all these contributions over all these intermediate states. And so let's assume that we have here this coupling strength, which you can write down in the following manner. What is important here are these constants EIM, EJM, which tell you how much ion number I participates in the collective mode N. This is the amplitude of motion if a particular ion oscillates in a particular collective mode of motion. So for the center of mass mode of motion of the string, all the ions move with the same amplitude, which means that all these BIMs, which I plot here, have the same amplitude. And therefore, the resulting spin-spin coupling matrix here will be an all-to-all coupling if the spins is antikinetic. Now I can add to this contribution the contribution of the mode next to it, which is this tilt mode of motion of the ion crystal. In this case, you see that ions which are close together they move in phase, ions at the opposite end of the string then move out of phase, and the coupling strength depends on where the ion sits. And now this gives a contribution which is no longer all-to-all. If I add this contribution up, you see that now the coupling matrix gets some structure. And I can add more and more of these motional modes, and in the end, I arrive at a spin-spin coupling matrix which is more or less homogeneous across the ion string and which falls off with distance. And to a good approximation, this coupling matrix can be described by a power law interaction, where you have then some coupling matrix that depends on the distance between the two qubits you're looking at, with some exponent alpha, which is constrained to be between 0 and 3. Now, we can then realize this spin-spin model, which would be the Ising model, and we can have some control over this exponent here by the laser detuning and also by the spread of these radial modes of motion in frequency space, which depends on the exponent. Yeah.
Just to make sure I understand, so if you add more lasers, you can make that matrix look however you want.
However I want, I think it's probably challenging, because if I have, let's say, if I have 100 ions, then this matrix has 5,000 entries that I would have to control, so this would be
But you get more legal.
Yeah, so you can modify, yeah, I would say you can certainly modify the matrix to some extent. At the moment, we try to work with the basic version because it's easier to control just one pair of laser beams instead of having many different ones. So our approach is to have, for the independent interaction, to have one laser field that couples to all the ions, give up control, let's say, give up a bit of quantum control, in contrast to colleagues of mine that are interested in quantum computation. In these experiments, you cannot just say, pick a pair of ions and say, now I want to have maximum entanglement. Let's say, quantum gates the table quantum gate realize between just this pair. But then on the plus side, it's easier to control large ensemble lines. Yeah, so we can also realize something like an XY model. In this case, we slightly detune the lasers to one side, and we get a transverse field Ising model. And in the limit where the transverse field term is much bigger than the spin-spin coupling constant, we suppress collective orbital spin flips where both qubits start off in the same state, and we just have this flip-flop term that survives in this case. And so then we get this kind of model that we have some hopping of spin excitations that we can look at. Now, does it work if you prepare, for example, this state of ions where you just flip the center ion and have this XY interaction, and you can switch on the interaction, you should see that the hopping of these spin excitations. And this is what you can see here, where you just look at the magnetization in that direction as a function of the size of the ion stream you're looking at. You see that it's initially localized, excitation starts to spread out, and there's a Fourier pattern that builds up to show that there's constant coherence. Now, this is very easy to calculate because there's just a single excitation localized over, delocalized over n sides. It's much more challenging if we start out, for example, with single state. If we can prepare now with our strongly focused laser beam, that every second ion is in the non-reversing state. And then we switch on interaction, you see that you get some popping of interactions. Here in between, we can show that you have entanglement between all pairs of nearest particles, but then at some point the magnetization signal goes to zero because we have entanglement which spreads in the system, and then it becomes much more challenging to try to understand what kind of quantum state we produce this kind of interaction. So, what I want to show you now is the first experiment where we, let's say, explore larger scale entanglement in the stream of ions. In the generic setting is that we want to look at some spin lattice model that's described by Hamiltonian, which is a sum of local terms. Let's assume that we prepare a particular quantum state psi of using this our resources, spectral Hamiltonian, and want to do measurements now in a sub-ensemble of our qubits in order to find out, for example, about entanglement that might be in the system here, which if you just look at sub-ensemble, then you might want to look maybe at the entropy of this subsystem that results from breaking entanglement in our subsystem we're looking at and its components. Now, and we do this in the context of variational quantum simulation. So in this approach, let's assume we put it in some target Hamiltonian that we might not be able to realize with our quantum resources that we have in the experiment. So depending on which experimental platform you use, there are a certain number of Hamiltonians that you can easily realize, and for such ions, for example, it might not be possible maybe to realize a Hamiltonian that we want to look at with our resources that we have at our disposition. In this case, for example, would be this XY model, this long-range XY model, together with collective spin rotations and some local controls that we have that we use from the focus. But what we can do is we can use these resources in order to produce a family of variational states, which are characterized by some angles theta that result by applying a couple of these operations in time to produce a state or a class of states which hopefully is maybe large enough such that it encompasses maybe the ground state of Hamiltonian, or at least prepares a state which has a sufficiently good overlap with the ground state of the Hamiltonian that we might be interested, that we want to investigate. So what do we have to do? So we have our computer that we use in order to calculate the, let's assume we want to find the ground state of a Hamiltonian system, then we can write down the excitation value of this Hamiltonian with respect to the variational state that we produce in the lab. And if the Hamiltonian is the sum of local terms, it means that we have to measure excitation values with spin correlation with respect to the quantum state that we produce in our experiment. And for this, the control program tells our experimental system to produce a particular state described by the set of parameters theta. So we have some layers of operations that we apply to the initial state, we end up then hopefully with the desired state on which we then carry out measurement. So we might need some additional local rotations to calculate spin rotations. We get measurement outcomes which vary from shot to shot. From this we can estimate the expectation value and then move on to measuring the next expectation, next observable that we want to know, which requires measurements in a different basis. And with all this information, we have some estimate of the energy of the Hamiltonian with respect to the state that we produce in our experiment, and then the computer can, based on the record of measurements that is available, the computer can suggest a different value for this vector theta. And so we have a back and forth between the computer, which tries to do some minimization tasks, and the experimental system, which provides the measurement data for this approach. And this is something we have done a couple of years ago in the context of a different experiment. Where you can see here we have some Hamiltonian whose energy we try to minimize, and this is sort of the number of iterations of this process here. And you see that we have now a search space with about 50 graphs in this case, which might have local minima, so the program has to explore different regions so that you find hopefully the global minimum. And you see that when the outcome is that you get here the energy which comes fairly close to the energy of the model, which is easy to calculate, which is quite a bit lower than the second stage of the model. Now, we have now done a similar experiment recently where we looked at a different target Hamiltonian, which is the nearest neighbor XXZ model, which is written down here. And using this approach, we see that we start off with initially some high value of energy, and we end up with a value which is low, still above the value, once again, which is known if this downside of this Ising spin we pick up, but we come at least sufficiently close to we prepare low energy states with respect to the Hamiltonian, and this is now for us a starting point to find out more about the structure of the state prepared this way. And so what we want to do now, the next step, is to look at the sub-ensemble here of the spins that we have in our system and investigate the state of these spins. And for this, we want to look at subsystems which are too big for full tomographic reconstruction of the system. So let's say maybe we want to do subsystems up to 20 qubits. And in order to do this, it means that we have to put in we have to use some parameterization of the density matrix, since we cannot do a full reconstruction. And it turns out that a good way to parameterize the density matrix is to first write it in terms of the so-called entanglement Hamiltonian. So every density matrix you can write in this way. I think here some Hamiltonian, which is called entanglement Hamiltonian. And this might look a bit artificial to you. And you might wonder why should I then maybe parameterize this entanglement Hamiltonian instead of parameterizing the density matrix. However, this is a natural way to represent quite a lot of quantum states. You think about a thermal ensemble where you have a canonical, so to say, the canonical ensemble, you know that then this entanglement Hamiltonian is basically nothing else than the Hamiltonian itself multiplied with the inverse temperature beta. So interestingly, there's a connection between this entanglement Hamiltonian and the system Hamiltonian that gave rise to this thermal state. And there's another example which is in the context of relativistic or conformal field theories, as in Ising-Wishman theory, which states that in this case, if you look at a sub-ensemble, you prepare the ground state of such a theory, then the entanglement Hamiltonian also has a structure which is very similar to what we have for this thermal state. So here you have an entanglement Hamiltonian, which is the sum of the local terms that make up your system Hamiltonian, multiplied by numbers which look a bit like a local temperature, and which might, for example, reflect the fact that if you prepare a ground state, which is Hamiltonian, and now you look at a sub-ensemble, and then you might create more entanglements at the border of the system than if you are here in the bulk of the sub-ensemble that you're looking at. This way, the inverse temperature might indicate how much quantum correlations you have broken by focusing just on a subsystem. And so this is what we have done now with our experiment. We have this prediction, so this Heisenberg model can be described by such a conformal field theory for the low energy states. And the prediction is that these betas take on the shape of an inverted ground. And so in this way we can now parameterize our entanglement Hamiltonian by these betas and carry out the measurements in order to determine these beta values here. And based on measuring correlations, spin correlations between sub-ensembles of this system here. And what we find here is a nice agreement, it's a prediction that we have indeed something which looks parabolic, and where the inverse temperature goes up, which means that the bigger the system you make, the purer the subsystem gets. And this is in contrast to what you have when you prepare a different state, which is not a low energy state. And then if you have an excited state here, then you find here a reconstruction which looks and feels that the structure is more like what you would expect from something for a third state. So I will not say this is a third state, it's far from a third state. And based on this, we can also check how well these reconstruction works for our sub-ensemble. We can look at the overlap between what we expect to find and what we have, and potentially add additional terms here. It turns out that this parameterization is not good enough. And then what we can also do is we can calculate the entanglement entropy here, and what we find is that for the ground state we have something which looks a bit like an area law, whereas for the excited state the entanglement entropy increases the system size more like the Yeah, so much for this first experiment. I want to years and briefly talk about the different experiment also done with ion crystal. And this is more in the field of quantum metrology, where you, for example, would like to use an ensemble of qubits in order to sense some quantum rotation of your collective block sphere here. Assume that that rotation of the collective block sphere. And if you have a product state, then this product state is described by a block vector, but the transverse spin projections have a non-zero variance. And this limits then the resolution with which you can measure then block sphere rotation using a finite number of experimental repetitions. To overcome this, you can now start to entangle the particles, such with the goal that this uncertain energy that you have, that you squeeze it in one direction and at the expense of expanding it in the second direction. And such a squeezing operation can be done by one-axis twisting Hamiltonian, which is a Hamiltonian where you have a spin-spin Hamiltonian with infinite range. And if you apply this, you see this Hamiltonian for every amount of time. You see that this circle of uncertainty here gets compressed in one direction and stretched in the other one, and this is then potentially a quantum state which enables you to do more sensitive measurements of such rotations here. Now, this one-axis twisting requires also Hall actions which might not be available in the system of interest that you have. And therefore, it's interesting to see that this spin squeezing can also be achieved with finite range interactions. This was shown recently in this paper here. And this is what we want to demonstrate in our experiment. So clearly, with our linear chain, we have not also all the actions. If we couple in terms of modes of motion, this is a measurement here of the spin-spin coupling matrix here for different ions. You see that the interaction here falls off rapidly with distance. And nevertheless, we are able to observe spin squeezing, which we measure by starting out with a collective spin oriented in the equatorial plane, that's then squeezed by applications of Hamiltonian for a variable amount of time. And if we measure then the variance of the spin projection in the transverse direction to the collective spin divided by the total spin length, so the Weinmann squeezing parameter, we see that we can get the value of the parameter which goes below what you can get when the state has no entanglement. And then at some point it starts to go up again, and this is the fact that you have interactions which give rise to more complex quantum correlations which cannot be captured by the spin-splitting parameter, and that's something you can also see in the experiment. If you measure this uncertainty and one of these strings to two-dimensional planar crystals is of interest with respect to two objectives. The first one is to add more and more ions to your system, which would mean that if I have a linear string, this linear string will get very long. Because as I add time, the string has to get longer and longer. But on top of that, if I keep adding ions at some point and keep my potential fixed, at some point it is no longer advantageous in terms of energy for the ions to arrange the linear string, and then the linear string will break up into a more complex structure. To keep the string linear, one has either to increase the relative confinement, which is very hard, or to weaken the weak confinement even further, which makes the strings even longer, which leads to lower frequency nodes, and also to technical problems like heating of these vibrational modes by fluctuating. And therefore, I think it would be, I think we might be able to trap 100 ions in our system going to 200 or 300 the linear string would be very hard. So why not go to two-dimensional crystals? And this is an experiment that was developed in the PFC project. And so it's easier to scale the systems up to larger ion number. And also the arrangement of the qubits is inherently two-dimensional, and so you have a different geometry of the spin Hamiltonian that you can easily realize with these laser interactions. So how can we create qubits with crystals of trapped ions? There are a couple of approaches. There are so-called penning traps, which use strong magnetic fields. And in these penning traps, people have demonstrated planar crystals of 100 to 300 ions, and some spin squeezing, also all interactions. However, the problem is that these crystals rotate rapidly. So you have crystals that rotate at rates of tens of kilohertz, and so getting single-qubit control will be very hard with these systems. The second approach is to use an array of radio frequency traps where each ion is trapped in its own trap. In this case, you have complete freedom about arranging these ions if you design your ion trap in the right way. However, in order to get interactions between the ions have to be close, which means that the trap electrodes also have to be very close to the ions. And then you have surface science problems which gives rise to strong fluctuating electric fields which can very negatively affect the coherence of the motional states. So there are no experiments at the moment that show entanglement in such trapped ion areas. And the third approach is to use just, let's say, standard radio frequency trap and to modify the anisotropy of the trap potential. And in this case, you have to live with the so-called micromotion. So in these standard linear radio frequency traps, there's a line of points in space where the ions do not experience any rapidly varying electric fields that are used to produce this confinement. If you have a planar crystal, then ions necessarily sit at locations where they experience this driven motion. This is called micromotion. And you have then to find ways of dealing with this micromotion which can otherwise complicate the laser ion detection. You don't want a doctor shift because the ion is moving to the laser beam. And so the planar crystals have been produced already 20 years ago, but only more recently have people shown that you can get realize spin models in small systems of ions trapped in such a planar. Now, what we have done now to create planar crystals is to design a new monolithic ion trap, so a glass substrate that is structured with laser pulses, femtosecond laser, and can then be gold-coated. And this way you have a number of electrodes which are very well defined in position with respect to each other, to which you can apply radio frequency signals, but also DC signals here in order to shape the potential in a way that is good for producing these planar crystals. Now, what are the crystal configurations you can have? if you look at such a picture here, you see that the ions, they arrange themselves in a kind of triangular lattice. However, the lattice constant is not the same across the entire ion stream. And therefore, there are always some kind of defects. So most of the ions have 6 neighbors, these 2 just have 5 neighbors. And for this reason, there are metastable structural configurations of these ion crystals. And it would be very problematic if you have now very many of them at low energy, such that you never know what kind of structural configuration ion crystal will have under those conditions with the background gas molecule as we have in our vacuum system. So one question was how many distinct configurations we often do they occur, and what one can do is one can take series of measurements and tell the picture of such an ion crystal, you analyze them, do a kind of clustering in some lower dimensional subspace, you find that at some distinct points, each of which corresponds then to a different structural configuration. In these pictures they look very similar, but here just highlight those ions which have 5 or 7 neighbors. You see that there are different configurations, and so maybe it's problematic to then know where to send your laser beam to if the ion crystal is not always in the same configuration. But fortunately, it's possible to play around with the isotropy of the confining potential in these 2 different ion directions, and then you find situations where in more than 99% of the cases you are always in the desired configuration. So this is then a good starting point for experiments, and it's easy to detect experiments where the ions ended up in the wrong configuration. So this is good for us. Now, in this case, we encode our qubit once again in calcium ion. In this case, we work with the electron spin of the ground state, so we have the ground state qubit that we can couple either using a radio frequency coil that produces an RF field that couples then all ions, or importantly, we can couple it using a Raman line field that off-gravity couples these 2 levels to the excited piece. And in this way, we can then induce collective spin rotations in all ions. We can use these Raman light field to produce entangling interactions by in this case coupling to the out-of-plane modes of motion. In order to measure this qubit, you have to transfer one of the qubit states to this metastable state before you use the fluorescence measurement technique. And you can also then use laser pooling techniques to pull all these transfer modes of motion to the ground state. What we're still missing yet in our experiment is single ion addressing. This is something we hope to add here. And what you can see here is the spectrum once again, these motional modes of motion, 100 ion crystal. If they are not well cooled, then you see that each of these modes has a resonance in the spectrum. As soon as you cool these vibrational modes to the ground state, you get this blue line here, which tells us that the motional modes are very close to the ground state, as we want to have it before we can start inducing the components. It's a bit more technical here. We have this ground state qubit. We see that the coherence time of the ground state qubit is very long. So once we cool these modes to the ground state, we have rubber oscillations that go on for a long time, which means that we have good control over this qubit. And if we just carry out measurements of coherence time, we see that we have here coherence time in the order of 200 milliseconds with Raman interactions, which is orders of magnitude longer than the duration of the experiment. Now, for quantum state detection, these are pictures that you get, for example, if you want to analyze the quantum state of these ions here, and for this we developed some, using some statistical method, independent component analysis, a tool that enables us then to carry out measurements where we then, for each ion, basically we get a distribution which consists of 2 parts, and where you can discriminate them the number of counts that you have to assign the ion being the bright and the dark state. Now, recently we have looked at the build-up of correlations, quantum correlations, using an Ising long and Ising interaction in these planar crystals, and this is what you see here. So we have this Ising Hamiltonian to prepare the ions initially or the downstate, switch on in Hamiltonian for a very amount of time. You can see that the build-up of correlations between pairs of particles, which are mostly local correlations. So the time going down, you see here, if you look at the outermost ion, then it gets correlated with its neighbors, but not with ions the other end. And what we see also is that we have a decent match between our expectations of how these correlations should develop in time, these curves here, and what we measure in our experiment. Now, in order to prove that we have indeed entanglement in a 100 ion crystal, we turn to this spin squeezing technique, as we don't have yet this local control to detect entanglement between pairs of particles. And so what we have done now is to once again use this transverse field Ising model in order to produce spin squeezing. If we can detect spin squeezing, we know that there is entanglement in the system. And what we see here is that indeed we have entanglement. We have more than we found for these linear ion crystals. And you see that these distributions of the magnetization that one measures, they get narrower than what we get when we have unentangled particles. And so we now know that we have entanglement in these systems, and what we are also now trying to do is to see whether we can now improve the amount of squeezing by once again using variational techniques in order to prepare a gas state which has even more squeezing than the simple one-axis twisting model. What we have done so far is to do a two-parameter optimization, which is basically the duration of this squeezing pulse and then a rotation of collective rotation that sets then the direction in which we hope to measure the minimum variance of these transfer spin components. And you can see here that here we have, this is our search space here, which is just dimensional for the moment. And you see that this algorithm then starts to explore the certain regions, the red points, more often than other regions. And if you look at the squeezing that you get, then you find the squeezing, which is a nice starting point for further experiments. So, to summarize, I told you about variational quantum simulation, where we have now used this variational approach to prepare the scenarios for Hamiltonian, we can directly prepare in the lab and to confirm this confirmation versus prediction of the Ising-Wichmann theory. We have seen spin squeezing, this fine variation interaction in these long strings, in these experiments with linear ion strings. We hope to update our apparatus so that it can also work with maybe 100 ions in the linear string. And with these planar crystals, we have now good control over these planar ion crystals. We have recently seen entanglement and also string squeezing with large 2D crystals. And what is still missing at the moment is the single qubit control and also the demonstration of more complex quantum operation in these systems. With that, I thank you for your attention and I look forward to this.
Thank you. We have time for a few questions before lunch.
Thank you for the beautiful part on the Ising theory. The limitation of the experimental data to smaller systems was because you need something like full-state tomography, so too many measurements.
Yes. Yeah. So if you wanted to look at a 20 qubit system, I think you would need measurements in, I don't know, a billion different measurement bases, which is completely out of question for us.
And so it's not even like thinkable to scale it.
Yeah.
To that.
Question.
Thanks. Really nice results on your improved spin squeezing in 2D. How much further do you think you can do to some extent? But is it theoretic? Have you got a number for what you expect to see, or is it really just a question of finding the right variation parameters to keep pushing the system?
Yeah, I mean, there are predictions that you might, if there was no decoherence in the system, you might get to something which is close to high-fidelity scaling. And then it depends on the number of qubits you have in order to estimate the gain. I will not claim that we get there, but we hope to make some, to show some improvement. Also, what is not entirely clear at the moment is how well we can, at the moment, use numerical techniques to predict the outcome of these experiments. So for the linear strings, there are these DMRG techniques which are well suited for the 50 ion crystals. For 2D systems, this will be more difficult, and there are approximation techniques which might be still good enough for squeezing, but we don't know yet.
So I have a short question for Well, what's the possibilities for looking at simulating dynamics, and then you need to get more information out by imaging or by some method. So,
Well, I think we always have one measurement step, and after this measurement step, we need to start again from scratch.
yeah.
But at least in the rate at which we can take measurements is fairly high, so with this distance here, it's not, we can take 1 million measurements per day, for example.
Okay, great. Last question from me? If not, don't disappear for lunch instantly. There's 2 short announcements to make. So, let's thank Esther again for your